Hello and welcome to the 7th tutorial of the called primitive science. So today we'll spend most of the time in coding different algorithms, which will include first we'll do something which is overdue, policy iteration algorithm. Next, we'll code value report 3D learning. We'll only do the policy evaluation part of 3D learning. This will not do learning and control both things. The control part is once you are able to evaluate a policy in this 3D learning algorithm, then it will be your job to incorporate the control part using whatever. And then we'll code two learning algorithm. So while coding this algorithm, we'll also introduce to gymnasium environment. So gymnasium is basically one Python library which contains lots of reinforcement learning and those environments can be used as benchmark different reinforcement learning algorithms. So that is one essential thing you want to carry on your work for the applications of fluid. So we'll just introduce something basic and then you can explore. So first is policy iteration algorithm. If you remember, policy iteration algorithm is planning algorithm. Right? You know the true MDP. That is, you know the transition probability kernel and the reward function. Let's see. Planning algorithm. Where you know the transition kernel and the reward function, and you want to design the optimal control and control law, and you want to evaluate optimal policy, that's optimal value function. So what is the algorithm? These are covered multiple times, but I'm recalling so that it will be easy to understand the code. So while you start with the policy, start the P naught. While first step is evaluate policy. Evaluate P naught. Find the fee. I think I was writing upstream. PC not and then improve this. That is, sorry, shouldn't write phi of k. K equals to 0. That is the k plus 1 is the such that the k plus 1 is argmax is basically the action which is maximizing the if pk plus 1 is to pk, then return. So if you need another step, that is k equals that's the algorithm. Now let us shift to string part. You can see the screen. Okay, so up to this part, this value iteration is now from here we start to. So we have seen there is one particular step which is called, if you are given a policy, you have to evaluate the policy. So given phi k, you have to find p phi k. So for that, we already know that we have two algorithms. One is matrix inversion test, where v phi is equals to I minus gamma times p phi. P phi is the transition probability matrix induced by policy phi. I minus gamma p phi inverse the entire thing times R phi. R phi is the reward vector induced by the policy phi. So this first function, policy well underscore mat, that is evaluating the policy, input policy, using this particular method. And there is one iterative policy evaluation method which is based on the value iteration algorithm, where you do not take max over all actions. Instead of taking max, you just fix your action to be the action which is being prescribed by the policy itself. So if you go through these two functions, it's very easy to understand. So these two functions are doing the doing exactly the same thing. They're given a policy, they're evaluating the policy. What are the inputs? The MDP itself, that is P and R, and the discount factor gamma and the policy. And in this policy evaluation matrix-based method, that is giving you the exact answer in one step. But the policy evaluation iterative method, that there is since this iterative, there will be some error, which is if that goes below certain threshold, that is very small near zero, then you say that, okay, we have got the value accurate enough, so you can stop the evaluation process iterations now, and then you can return. So that's why this policy evaluator that takes another parameter epsilon, which we have kept by default 10 to the power minus 10. Right. So now it's just testing on these algorithms for one policy. Let us run the codes. So these are for finite horizon. These are for infinite horizon. This is initializing the MDP. Value iteration you do not need. So we are initializing a policy, which is just some randomly generated policy. Then here in val underscore one, we are calling this evaluation iterative based method. And in val underscore two, we are calling this matrix based method. So I'll print this two. Let's see if they're giving the same. They're giving exactly the same things. Maybe there will be some decimal difference in decimal places after 6, 7, because one is very accurate and another is iterative. However, we want to compare these two algorithms uh, based on how much time it's taking. So intuitively, the matrix-based method is just one step. It's inverting the matrix and there you go. We have the result. Inverting and then multiplying the vector. So it's just one step process. But iterative method, we do not know how many steps it will take. So it may take much time. So here what we are doing, we are running both the algorithms for 20 times and averaging the time taken and printing it. Let's see how much. So here you see that there is a huge difference between two algorithms, average time. The iterative solver is taking 0.09 seconds. So it's 97 milliseconds. And the direct solver, the matrix space solver, is taking 0.3 microsecond, sorry, millisecond. So that's quite a big difference. 97 and 0.3. Okay, so it's very clear that we will use the matrix-based solver in our policy iteration algorithm, where we'll be using this policy evaluation algorithm multiple times. For every iterate, A, we have to evaluate B evaluate. Okay, so this policy iteration algorithm is taking input MDP and gamma. We're initializing the policy, which is some random policy. So here we are in this step, we are copying the old policy to policy underscore old, and then we are evaluating the policy. That is the old policy. We're saving the policy in some other variable so that later you can compare with the newly generated policy. So in V, we have the value function of the particular policy. And for every state, we have to generate now new policy, right? So in policy, now we are saving the newly generated policy. So that is this particular step. And after this step, after this for loop, we have the new policy generated. And if the uh, new policy is same, that is checked in this if condition, we have used this inbuilt function array equal in NumPy. If they are same, then we'll break. Otherwise, we'll continue for another iteration. And we'll at the end we'll return policy and value the optimal policy. So let us run this algorithm. So here you see it is giving the optimal values. But now we are comparing value iteration and policy iteration. Again, for 20 times we are running value iteration and policy iteration, and we are printing the average time taken. Let's see what is the difference. Okay, so I have not run value iteration yet. Now that we have run value iteration, let's see how much time does it take. Probably it will take 1 minute or so next time. Okay, so here also there is a huge difference. One is taking 0.6573 second, and another is taking policy iteration is taking much less time. 0.0414. So policy iteration you're seeing that for this particular example, policy iteration is uh, much faster. Okay, so we are stopping here. Hope you have understood this algorithm very clearly. Now we'll move to TD learning. We'll do a recap on PAD and then we'll start coding. So as I have said here, that we only looked at the policy evaluation part of TD learning. The control part you have to it's your task to complete the algorithm with the control part. Right. So here is the algorithm. Input is MDP self and the policy. To initialize, we had as we have zero. It's all zero functions. So here, this is a function. So I should write v hat s equals to 0 for all s. Well, now you start running this algorithm for certain time steps for t equals to 1 to capital T. So every time you get so two things are fixed, right? You observe state st and take action according to policy. I'm not writing you take action PS because this policy fee could be randomized. And then you update the hat. So here I'm writing in E ST, which is basically how many number of times you have visited state ST till time T. So you update that using this particular equation. We have in T minus 1 ST plus some alpha in ST or T, the reward you have got at that particular stage, plus gamma times V. So you have also got the next statement. So in T is T plus 1 minus V in T plus 1 T. That's your algorithm where to define certain things. NT is S equals to 1 to T indicated S equals to S. S. So SS is a bit confusing. Let me replace S by tau. Tau equals to 1 to T. S tau equals to S. Did. So that you do till time T and the end you have some estimate and that's your value estimate at the end. Okay. Now let's move to the Jupyter notebook and try to code this algorithm. Right. So we'll copy the MDP we have created for the infinite horizon problems. Right. Or let me just hope you can see the copy the MDP. copying the all the necessary codes now. Policy evaluation is also I'm also copying that because we have to compare the value that we are learning through this TD learning algorithm uh, to our, I mean, we have to compare it to the true value, right? So we'll do that as well. Initialize the policy, we'll evaluate the policy through policy evaluation algorithm, and then we write the code for 3D learning algorithm and we'll see how they match or how much they differ. So we have a random policy and we have its value. Now we have to write this TD learning algorithm. We have to pass the policy and then and see, and also the discount factor. Yeah. What is the first step? We have to initialize the value estimate. Let's write it as p hat. And that is how I think we saved it in yeah, this kind of array. So how did we run this MDP? So first we reset. Our state is initialized according to some updates. Our state is initialized with randomly under uniform distribution. That's what this particular line is doing. And then upon taking, you have so you take every step at every time, and you pass to the step function. You have to pass the action. Great. So that's what it is. Feeding on MDPN. So for so we have a horizon as well. So some capital T for T in range capital T. First, before starting this, you have to reset out state is m dot reset. Then at the beginning of that particular uh, time, we assign the state value to the next state variable. Okay. And then we save state reward. and what else. So the reset step function is returning state and reward. That's it. That is equals to m dot state action. Action is specified by the policy, right? So policy sorry, I did a bad mistake. So we first start with next state and then in state variable, we assign the next state variable. So what was next state in my previous state? That is state now. And then here we generate next state by taking the action. Then we take action according to the current state variable and whatever the policy is prescribing to act at current state. Well, so we have this pair state, next state, reward. That's all we need to update the estimate or V hat. Or is there anything else? Let's ask that question because I think we need something more because we need also the count how many times the state the next state those are visited. So here since we are visiting the next state at this particular we are visiting state, right? Okay. So let us update the count. It's n. And this count of how many times the state is visited. Initialize it with 0 and end state plus equals to 1. So whenever state is visited, you increment it with 1. That's all you need. Okay. Then you update V hat. Skip a line. V hat state. You update that using V hat state. It's not so you do not need this. You can just write plus equals to alpha NTST. So alpha NTST, that theoretical analysis those are done. That shows that if we take it 1 by NTST, that that would be nice. I mean, in that case, if some properties are other properties of the MDP are satisfied, then the in infinite horizon the V hat will approach to will converge to true value of the policy. So we'll take alpha NTST as 1 by NTST. So 1 divided by n state times the reward we have got that particular state reward plus gamma times V hat of next state, right? V hat of next state minus V hat of current state. That's what is the update equation. Great. So next, what we have to do, we have to, I think that's it. We do not have anything else. And then we have to return the hat. Well, so uh, what we do not have is this capital T. Let's keep it 1 million. Then, so that's it. So then we have to call this function p at policy. Gamma is also initialized, right? Write it out. Some error. MDP has no actually. Okay, so it's not MDP, it's single. Everywhere else it's let's see. Okay, so int object doesn't. We import on the function. Sorry, on the library. So it's running. It will take some time because T is quite large here. And after it completes running, then you have to print the estimate. Ideally, this should be whatever will be printed here should match very closely to this pair. It has not at all matched this. So there must be some problem there. Oh, sorry. So these policies are not same, is it? Let me run 1 second. Shoot. So there is some problem for sure. Okay, so something is not right. So this relatively this is the same because 8. There's definitely some problem. I'm not sure what is happening, but the relative values, if you see, those are same. And I think we have to run this algorithm for quite uh, longer time. Since we are initializing it with all zero vectors, probably that's why. What if we initialize it all once? still it's okay. What if we do the following? If we run it for 10,000 or 1,000 steps, so 10 to the power minus raised to 0.9 raised to 2,000 and with minus 5. So what I'm currently doing is we are truncating each episode at 1,000. So since this is gamma discounted problem, in the last tutorial, we have discussed that uh, if we truncate the episode at certain point of time, if it is quite high, then the tail sum will be very less. And if the tail sum is negligible, then we can actually truncate this gamma discounted problems. So here what we'll do is we'll, we'll truncate this at 1,000 and this particular thing. So this is one episode you can think, and this particular thing we can compute multiple times for multiple episodes for a in range capital A to this and initial is k. Sorry, let's assign k to 100. Let's see. So 100 times 1,000, so it will be 1 million. So what I understand is it's pain is increasing very rapidly. So what we can do is also this is an visible option, that is we make some sublinear power, like in state raised to 0.55. We cannot go below 0.5 for some theoretical reasons. 0.55 instead of 1 by n. We are reducing that value 1 by n. Well, now it seems it has increased quite a bit. Nice. Let's see what happens with 0.5. So theoretically, it's not permissible, but great. So one of the reasons why it's happening is since there are less states, every state is visited lots of times. So if we increase the number of states, then I think we'll be in a better position. So let's increase it to say 30. It will take more time. Now hopefully it will take. No, unfortunately, that is also not being true. What if we do the following? Instead of multiplying, taking any power, what if we just multiply something? Sorry, instead of 1, here if we write, say 10, similarly here, 10. So there will be some problem there. And so I think we have to deal with this problem by taking large, uh, value of t or k, but otherwise I don't see any problem. So here I have increased k 1000. It will take more time, but I hope that it will be closer to the true value. Great. It is much closer. If we try with higher value of k, maybe it will give much better results. So it will take some time to run. Meanwhile, we can discuss the Q-learning algorithm, and next we have to code. And when we come back to code the Q-learning, we will see the result of this part. So first of all, why we need Q-learning? What was the problem in controlling according to this uh, 3D learning, where we are estimating the value function. Why? So Q learning does this estimate the Q function, and why we need that estimation, right? The reason is the following: you can write two Bellman equation. One, uh, I think I'm sure that you are introduced to, that is with V function, value function. So Bellman equations. First one is V x equals to x over actions, or let's say was expected next state values. So this is the Bellman equation written in terms of values. Now, what is the relation between value and Q value functions? So whatever we have written inside, that is Q value function, right? Whatever is inside the max, that is Q. Correct. But how to write this uh, as in the form of Bellman equation? Okay. So to replace this B, right? The B is, Q we can write in terms of this inner uh, inside that max operator, right? So Q is A. It's A plus. And now, what is P as well? Can we write in terms of Q? Of course, we can. So R is A, that is equals to this time A prime. Can write, we cannot write A here, so we're writing max over A prime. So this one is the Bellman equation in terms of Q function. Now, when we have an estimate of Q function, so say at time t, we have estimate. So I'm not writing gamma here. Let me write that. we have estimate q hat t of q, and we have st. We have already taken action at, and we have st plus 1. So in the same way of TD learning, we can update this q hat t plus 1, or let it write nt stat. It's called a stat. That we can update as RT, the reward you have got, plus gamma times. Right. So this update is also TD update. You had NT minus 1 STAT plus alpha T STAT times RT plus gamma, then the expectation is not possible to do it. We know ST plus 1, so we know one sample of S prime. We can take max. Right. Q hat NT ST plus 1 A prime minus max A Q hat NT. So NTST plus 1 and all. Let's now go there. NT minus 1 ST. So this is exactly the TD update, but for Q functions. Now, what is the benefit here? So here, since you have an estimate of Q function every time, you have a notion of optimal action to be taken according to that Q estimate. You can act as your estimate is the true one. If your estimate is close enough to the true one, then actually you will be taking near optimal actions. If not, then you have to think something else. So the idea is you initially you do more exploration. That is, you with more probability you take explorative actions, and with less probability you pick the action which your estimate is suggesting to pick. So at time t, you have say. So this is about updating the estimate. What about taking actions? At time t, you have st and then you take greedy action with probability some function of time and could also be function of state with probability epsilon tst, or better to write 1 minus epsilon tst. Uh, and what is the greedy action? At is basically that is equals to argmax. Argmax. P Q hat. I'm not writing this. Uh, okay, let me write NTSTK STA and take exploded reaction with probability epsilon T XT. So initially your epsilon DST should be very high and we'll be taking more exploratory actions, and as time uh, increases, you take it's expected that your estimates are more closer to the true Q function, and you with more probability you take the greedy action. So that's the idea. So here the difference is, since you have the Q function, estimate of the Q function, there is notion of greedy action. If you have only the estimate of the value function, you cannot, given that you do not know the reward and transition kernel, which is obvious, you cannot take the greedy, you cannot, the word greedy action doesn't make any sense there. Okay, so given that now we know what is Q learning. Okay, so better if we, or you already know the algorithm. So from lecture, you know the algorithm. So we are not writing the algorithm explicitly. So these two steps are made. So one is you take with some probability, you take action, greedy action, with some probability, you take exploratory action, that is taking action part. And then after taking action, you have to update the Q-value estimate. After taking action, you will also receive the next state ST plus 1, and then you have to update the estimate. Okay, so that's it. Uh, Now we'll code Q-learning algorithm, and that will be the last thing to be done today. Okay, so here we have this result of the last run, where we have increased the number of episodes to be 10,000. And uh, yeah, so here you see that our estimate is tracking very closely. So let me copy here. So these two things are, so the only difference comes after two decimal places or one decimal places. Yeah, somewhere one decimal places. So that's quite close, quite close. And I don't think we can expect more from this city learning algorithm. Okay, great. So now your job is how, it's, I think, discussed in lecture, how to incorporate control in 3D learning. And that is not as efficient as Q learning, but I think you should try it, see. So now we'll code Q learning algorithm. Again, we copy certain things. So copied the infinite horizon MDP from 3D learning notebook. So here we do not need any policy evaluation or, as a matter of fact, any policy at all. So Q-learning algorithm will be very similar to this tree learning. So I'm copying this function. And so instead of V hat, we'll have Q hat. And the size of Q hat will be NS cross NA. And let me think if we need count of visiting a state action. Yes. So here we'll not do it for multiple episodes. We'll do for one long episode. So one thing to decide is how this epsilon will decay, or with which probability will peak action, exploratory action, and with what probability will peak greedy action, that we have to decide. Let's decide that we'll pick greedy action with probability uh, 1 minus 1 by number of times we visit a particular state. So here we let us write that x is 1 by state rather. So we are not counting how many times a state is visited. Okay, let's count both. Capital N is saving the number of counts to S, and capital N subscript S is saving the number of times a state is visited, not a state action pair. Well, so N is state is implemented by 1, and then X is the number of times, 1 by number of times you have visited a state. So if a state is visited very often, then we can, I mean, it's expected that the state is, uh, all the actions are explored enough number of times, and hence we have very good estimate of the Q function. Let's also take some power of in it 0.5 say 5. Okay. Well, uh, now we have to take action, which will be either greedy and or exploited. So how will take that? So we have to generate Bernoulli random variable. And how do we generate Bernoulli random variable with probability 1 minus x or x? So let's generate a Bernoulli random variable with probability epsilon. If uh, NP uniform random uniform. So that is NP random uniform by default that generates a uniform random variable uh, that samples from uniform random variable from 0 to 1. So if that randomly generated number is less than equals to x, what does it mean? So from 0 to epsilon, there is one block, and epsilon to 1, there is one block. So with probability epsilon, the random uh, variable or the sample will be with epsilon probability, that will be 0 to epsilon block. And with 1 minus epsilon probability, it will be epsilon to 1 block. Right. So if this is true, that means it will be true with probability epsilon. With probability epsilon, it will be true, and with probability epsilon, we'll take exploratory action. Right. So there is a function already written with how to take exploratory action, that is sample action. Action equals to n dot sample action. Else, we take greedy action. Right. Action equals to argmax q at state. That is giving you one array, and whichever action is maximizing that q at state, then that particular coordinate will be your action. And then you take that action. There is the policy. Just copy it from PD learning. Then you take that action, and then you have to update q hat. Let's write the update equation. So now we use one by state action. Number of visits to state and action. You had state and action. Same here. So here we have to take a max. Max. Give it next state action or just A or A in. That's what giving us the Q update. Let's change the name. Great. I think this is it. Let's call this function once. Okay, so there is some problem here. Well, so what I didn't do is I have not increased this count here. Now let us print that. It will be very small because the strength is standing for very time. Right. Now let us do it for different number of episodes. Okay. Okay. Sure, what is happening? I know this. I have not initialized key. K is say 1000. It will take some time, but hopefully it will soon. Well, while it's running, let us look at the cumulative rewards that it's incurring in every episode. Okay, so cumulative reward. So since it's learning, we can expect that the sum of reward in every episode is also increasing. So here there is some feedback. Fine. Uh, there is no issue with that. But what I'm trying to do now is let us initialize an array cumulative reward. Sorry, a list. And let's write this episode rewards. Every episode, let us initialize uh, a variable cumulative reward as 0. And then after obtaining a reward, we will is summed by the reward. So this is not gamma discounted. I think this will also make sense. And at the end of the episode, so here, episode words append skill names for current given reward. So, and then also we reward, return episode rewards. So idea is the episode reward should increase. Yes, so there is a pattern. There is a pattern. So initially it's 0, then it's here it's increasing and then saturating somewhere. Well, it's not very convincing, but yeah, again, let's decrease this power. I think that will help. So by decreasing this power in by writing this epsilon, by decreasing that, we are ensuring that epsilon decays slowly. So it will take more exploratory action. So here you can see that the rewards are increasing. So from first episode it's around 650 and the last episode it's around 750. So by tuning these hyperparameters like epsilon and also this is also a hyperparameter, right? So how much weight you are giving as time progresses to your old Q values as compared to new Q values. So this depending on this rates and hyperparameters, your performance changes, and it's a nice exercise uh, to try different hyperparameters and see what is working, what is not. Yeah, so that's all for today's tutorial. And in our next tutorial, we'll discuss next topics, that is uh, function approximation. Uh, Setu, do you have any question? Okay, I'm assuming you don't have any questions, so I'm stopping recording here and we'll. Okay, you're typing something. Okay, so do you have any question? If yes, then you can type it. Okay, so thing is, if you can pinpoint some topics, then we can discuss that topic in detail. And also, I mean, before the tutorial starts, say on Thursday or Friday, if you, yeah, sure, sure. Uh, yeah. Yeah. And if you have any doubt from some topics, feel free to mail me, and then I'll also prepare that particular topic and try to clarify your doubts. Okay. So here is my mail ID. Okay, so we are ending today's meeting here and see you in the next tutorial.